all these things, it will be a little bit higher value. Higher value mean for 0.37 you will have 0.5. The lower the smaller the value of the resolving power. The smaller the value of the resolving power, the better is the resolution power of the microscope. The minimum you can distinguish, you can resolve, the better is considered the microscope. The Waluke features, the smaller feature you can resolve, the better will be the microscope. So the lower this value, the better will be considered the microscope. Right? Smaller features means better resolution. Now, come to we are moving a little bit towards electron microscopy. Gamma rays, their wavelength is up to 10 power minus 1 nanometer means 1 angstrom. 10 power minus 1 nanometer is 1 angstrom, right? In 1 nanometer you have 10 angstroms. 0.1 nanometer is 1 angstrom. And here 10 power minus 6 nanometer, it is about 10 power minus 6 nanometer. Say very smaller than angstrom. So when the wavelength of a radiation is below 1 angstrom, they come in the category of gamma rays. Then come down here, X-rays. They start from 10 power minus 2 nanometer.
Yes, sir.
10 power minus 2 nanometer means 0.01 angstrom. 1 nanometer over 100.
Yes.
Think over it. 10 power minus 1 nanometer. No, 1/10 of a nanometer is 1 angstrom.
Yes.
Right? So it starts from there and reaches up to here. 10 nanometer. 10 nanometer is about 100 angstrom. Most of the dimensions of the unit cells in crystals are in between 1 and 100 angstrom. In the organic longer molecules, monomers, they may have up to 100. People usually say up to 80 angstrom. From 1 angstrom up to 80 angstrom, all the interplanar spacings, all the lattice parameters of the crystals of the unit cell come in that category. So X-rays are ideal for crystal structure determination because the resolving power of this X-ray, the wavelength is of such length that it can resolve the interatomic planes inside the crystal. That is why X-rays are ideally used for crystal structure determination. To understand it in the simplest examples, right? Do you eat rice with spade? Pabeljewa nirujo pre? Wole. Hello, wala da belje luye la kana. No da belje mung sara luye. No da the unit cell planes resolve ki. So we need comparable size of the resolver. You use tweezer to pick small things, but you use forceps to pick big things. Then you use tractor blades to pick huge things because you need something comparable in dimensions with the one you want to resolve. The same thing is here. If the radiation wavelength is longer than the dimension you are investigating, you will not be able to resolve that. That is why you use X-ray commonly for that. Ultraviolet rays, which start from 10 nanometers, so above 100 and up to here, 1 micrometer. Right? Now, from here, the visible light start 0.1 micrometer, 1 micrometer. It is how many millimeters? 1 micrometer. 0.001. How many millimeters? So this is the visible range from here to 1 millimeter. Right? From 1 micrometer to 1 millimeter, it is the visible range. Beyond that, up to 10 centimeter. Here, 10 centimeter and 1 millimeter. This is the microwaves dimension, the wavelength of the microwaves. The microwave is the modern day game changer of electronic industry. Your cell phone, your radar system, your antennae, your global positioning system, all are governed by that millimeter wave and microwave. This range of dimension. Then onwards are your radio waves, long wavelength wave. And resolution is roughly half lambda. Lambda is the wavelength of the radiation. And resolution, resolving power, I will say resolution, is half lambda. So when the lambda is small, the resolution will be small or big. The better the resolution, the smaller the wavelength. Right? Better the resolution, the smaller the wavelength, the better will be the resolution. Now, all these radiations are there, and you can't go here in the visible range from 100 nanometer to 1 micrometer. The visible range. And the optical microscope is using that wavelength. Whatever you do, whatever hard work you do, whatever effort you do, theoretically, you can't increase and make the resolution finer than 1 micrometer because resolution is half lambda, approximately half lambda. So the maximum you can go when your everything is ideal, all the lenses, all the feature, electronics, whatever you gather together, you can't go beyond half lambda. And when lambda is fixed, you can't go below that. And most of the electronic world, the crystallography, the dimensions are in angstrom. And that was the failure of the optical microscopy. Understood why optical microscopy failed? Because of this, that the wavelength, you couldn't decrease it, you couldn't bring it down to enhance the resolving power. The fixed length, you can't decrease it. So you cannot measure features smaller than this. You can't resolve features smaller than this. You can't decrease the wavelength of that beyond this 100 nanometer. 100 nanometer na to निश्चित ले. Right? So you can't decrease the wavelength. When you can't decrease the wavelength, you can't enhance the resolving power. And that was the limitation of the optical microscope. And that is why people started to think about using other radiation for imaging. Right? That is why people started to think about using other radiations for imaging. Otherwise, optical microscopy had discovered half of the world. People had gone through down. They didn't know about the human cell, they didn't know about bacteria, they didn't know about many things. And the optical microscopy discovered all these. But the engineering of material was not possible because the unit cell dimensions were in angstrom and the optical microscope resolving power was in microns. That is why it couldn't do the work of the modern world. And that is just a picture of how half wavelength is the resolving power demonstration. Numerical aperture, I mentioned this word. In optics, the numerical aperture of an optical system is a dimensionless number that characterizes the range of angles over which the system can accept or emit light. I am holding this in front of me. When I am bringing it closer, I am increasing the angles. My eyes here. When I am bringing it closer, I am increasing the angle. So the numerical aperture can be increased or decreased. But there is an optimum value of the numerical aperture, which is the most suitable distance with which you have the maximum visibility. In the simple words, you can say there is a distance at which the feature can be seen in the best possible way, you can say. And there is the numerical aperture. So if these angles, they are coming in the next, that here, this is one medium. One medium, for example, air. Right? The ordinary atmosphere. The light is going straight. But there the medium changes. When the medium changes, the radiation diffracts, refracts, bends, or something happens to it. The air refractive index is 1. You can call it a free space. Is it free? It's not free, but we call it conventionally as free space. And its refractive index is 1. So the beam is not bent. But when it enters another medium, then it should go like this. But it goes like this or this. Upon exit, it again makes an angle. And these angles gather together in different media, and they will give you the numerical aperture is in. In is the index of refraction. Refractive index. And sine alpha is this semi-angle of the maximum, that optimum distance I told you. And numerical aperture is in the refractive index and sine of this alpha. Perpendicular is where? Alpha is this and sine of this angle. So if this angle is larger or smaller, it will change it. But that distance is almost constant, and you only, n is constant for any constant medium. For example, for air it is 1. For water it will be 1.5 or something. then it is constant. You can't play with that. Similarly, that angle gives you optical value at a specific angle. These are the refractive indices. So these things are all constant. Only lambda can be changed by changing the radiation. Right? Lambda can be changed by changing the type of radiation. The type of radiation are these. You have all these choices. This is your whole spectrum. Which lambda do you need for that particular application?